Thank you, Devavrat and Sandeep, for the kind introduction and invitation to come here. I prepared some slides, but this is a course, so I will use the board when necessary. So please feel free to ask questions if something is not clear. That's my first thing. Second, I don't know the audience background very well, so if I'm using terms and definitions that's unfamiliar to you, please stop me. I'll explain these to you. They're not really, nothing in this talk is more of an overview and trying to whet your appetite to this area. So I would like you to, it's more setting up some of the questions, setting up some of this context. There will also be some arguments, but they'll be mostly rather basic. Okay. So, and I'll tell you how these problems, this is the outline of the talk. So first I will introduce the area of network information theory. I know some of you are familiar with this, but I will introduce some of the building blocks. And the main focus is how to test the optimality of coding schemes. And in this, we will see where the optimization problems arise. That's the first part. And then I will look at two problems to illustrate some ideas. In between these two, I think I will take a break. And then there'll be a section on observations and potential future directions. Okay, so that will be the outline of the talk. So first we will see some building blocks and kind of make the setup of the whole problem. And then we look at some problems where some of the ideas have already been used in some sense, and then look at future directions. Okay. Let's start with the basic information theory problem of channel coding. So what is the channel coding setting? So you have a sender who wants to communicate some message to a receiver. He has some message M. He's going to encode this message into some sequence of symbols. This symbol goes through a noisy channel and produces an output sequence yn. The decoder will look at the output sequence yn and decode it to some estimate of the message M hat. Now I write this as W tensor n to indicate that the channel behaves in a memoryless fashion across time. And then we say that for such a setting, rate R is achievable if there's a sequence of encoding and decoding maps, so that the probability that the estimated message is not equal to the correct message goes to 0 as the number of channel uses or the block length goes to infinity. And the capacity is defined as the minimum over all rates such that R is achievable. So this should be, I'm starting slow. Hopefully, it's easy for people to follow at this point. So please stop me if you've not seen some of these things. So clearly Shannon developed this, looked at this problem, and he said he used random coding, really probabilistic method, to say that he can achieve a rate given by supremum of the mutual information for all input distributions mu of x. So if I give you the input distribution, and with the channel I know joint distribution, so that defines a mutual information ixy, where ixy is just the log likelihood ratio between the expected log likelihood ratio between the joint and the product marginals. And he said that I can achieve this rate. And the next question is it the best you can achieve? Is R of W equal to C of W? And we all know that, yes, he showed that in 48 that is indeed the best you can achieve. Okay. Yes. Oh, a rate R achieved means, so the message M will be in this set, 1 up to 2 to the NR. Okay. So you will want to send a message from this set to the receiver. So it's R bits per channel use. So that's how the message increases. So M is actually, M takes a value that depends on N, and that's the rate R. That's clear? Okay. So how do you show that? So here he has a coding scheme which he claims he can achieve by using a random coding. And the question is, how do you show that that's the best you can achieve? And this is the flavor of the whole talk. How do you show that certain coding schemes are the best you can achieve, that you cannot achieve something better? Or can you answer this question? Is this the best you can do, or can you not? Can you do something better? So here is how you test the optimality, and this is kind of the way I'm going to do it for other settings where we don't know the answer. It's easy to see, we'll see why, that the random coding rate is optimal if and only if I apply the random coding rate to a channel which is omega tends to omega, that means I take 2 independent copies of channel, the rate must double. If this is true for every W, then I claim that R of W is optimal. It's an equivalent characterization. Why is this? Clearly, if the channel W is such that this is bigger than R of W, then I can think of 2 independent channel uses as 2 blocks of time, and I can code across 2 blocks of time, and I can attain this rate for the original channel by just taking blocks of size 2 as one component. So clearly capacity is at least as big as half of R of W tensor W, and if this is bigger than R of W, then you have a contradiction, so which means that this is not optimal, therefore equality is necessary. Now why is this sufficient? So given any epsilon positive, we know from Fano's inequality is just saying that if I can estimate something with low probability of error, then the conditional entropy is very small. So we know from Fano's inequality that the normalized mutual information for a good sequence of codes must be at least C of at least bigger than C of W minus epsilon. If you haven't seen this, it's easy to show, but I hope most of you have seen this. This is kind of the building block. It uses 2 components, Fano's inequality and data processing inequality. And now what do? You just take an n large enough, you take n to be some dyadic power. We know that from induction, the R of W tensor W n times is equal to R of W, normalized one, and that's equal to 1 over n I of, that's the maximum of this, and that's bigger than C of W minus epsilon, which means that you need, so R of W is bigger than C of W minus epsilon for any positive epsilon, therefore R of W must be C of W. That's the argument. So in most cases, we will have using Fano's inequality, we will have the limiting expression to be true. So really, all you need is to check is whether the one letter, what I call one letter, is equal to 2 letters. So that scales. So to show this, so since R of W is the supreme over all mutual informations, it's enough to check if it will follow if I can show the following subadditivity. So which means, what do I mean by subadditivity? The same sense as what Varun is looking confused. In the same sense as what Varun said, you have a joint distribution on x1, x2. So this is a distribution on x1, x2. Going through independent channel, I want to ask whether this inequality holds. So here channel is independent. I want to ask whether this inequality holds, and this is what I mean by subadditivity for any function. So a function, there's a normal lift of a function to a joint space. That lift must be less than the sum of the marginal. Okay, now why is this true? This is true just from Markov chains. So you just do by chain rule, the first inequality follows. Then I apply chain rule again to get the second inequality. Now I know that the output y1 depends only on x1, so I can drop x2 here. I know the output y2 depends only on x2, it doesn't depend on the past, how it behaved previously. So I can drop y1 and x1. So this becomes equality. That's data processing, essentially. And now I know that this is non-negative, so I can drop it to get inequality. So clearly, the supremo on the left-hand side is less than sum of supremums. So therefore, you get R of W tensor W is less than twice R of W. That's the proof of the optimality of random coding. On the other hand, computing R of W explicitly is relatively easy because for a fixed channel, IXY is concave function of P of X. So it's a concave maximization. So that's also kind of easy. Okay, so this is not too hard. Okay, so that's point-to-point setting. Yes. Yes. No, that's okay. Yes. 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 It's an operational definition. Yes. Yes. So the question is, we want to check whether the random coding rate is the capacity. So Shannon showed that you can achieve this. And the question you're trying to ask is that the best you can achieve? And I claim that to test that, it's enough to check this equality. And how do you check this equality? By using this subadditivity. Okay. Yes. Yes. I mean, the mutual information in blocks would capture the best you can do because of finite because you know that the conditional entropy must be small, and then you know data processing gives you that. And those arguments in general expect, I mean, they are there very easily, and so you want to see whether they can get it. So essentially, it's some tensorizing phenomena of some large deviation functional. So yeah, this is some kind of rate functional, but we will see. I mean, so I think you want to see whether there's a finite dimensional rate function. I mean, computable. So really, what we're going to later look at is this problem will become non-convex for certain settings, and therefore computing things become harder. Yeah, yeah. Oh, the above equality is easy to see why. Yeah. No, the above equality comes from the subadditivity, right? Why? Because for every pair of distributions, you have the subadditivity, and R is the supremum over all IXY. So which means that supremum over all joint distribution gives me this, and that's less than sum of supremums. So you get, yeah, yes. Perhaps. I mean, I'm not sure. So, but it'll be nice to see it. I mean, to see something because. Okay. Anyway, so these ideas introduced by Shannon have led to a huge revolution, and a lot, and these random coding and optimality directly inspired LD. Go ahead. Yes. Yes. Proof of Shannon. Yes. Yes. Think point to point setting. Okay. So now, so you really, a lot of these components have inspired a lot of things. Like polar codes, really, if you look at the Arikan's argument, it comes from the proof of subadditivity. So he does this, then he does a plus and minus transforms, then he transforms it, and that's, so a lot of these arguments have led to a lot of nice things. But now we are in a wireless world, which means that we have not point to point, not telephonic communication. You have multiple users sharing same medium, and we need to maximally utilize power, bandwidth, energy. So clearly, there's a similar need for similar understanding in network settings, because there is, I mean, resource is always the limitation. But to understand large networks, you at least need to understand the basic building blocks. Otherwise, there's no hope on understanding optimality in large settings. So that's the goal for network information theory, to understand the basic building blocks of large networks. So let's take the first building block. So the first building block was initially considered by Shannon. It's called the multiple access channel. You have two senders who have two different messages. They want to communicate to a common receiver. So think of in the current day world, there are two cell phone users in the same mobile cell who want to talk to the same base station. So that's the setting that's captured here. And the question is, what is the set of rate pairs R1 and R2 that can be successfully transmitted to the decoder? So here, Rudy Al-Swedi said that, again, you can use random coding to achieve rate pairs R1, R2 that satisfy these three constraints. So there's a variable Q, which is kind of time sharing or time division. And for any set of, now it's a rate region, for any set of distributions of this form, you can achieve these rate pairs, and you take the union of all possible distributions, then you get some region, and you can achieve this region. And now, as coming back to the question, you can ask, is this region the best you can do? Is this the capacity region? Can you achieve something better? So, and this is again answered by Al-Swedi. Al-Swedi said that yes, this is the best you can do. So now let's see how can you argue this in a network setting. Network setting, you have to compare regions. So instead of comparing regions, I'm going to do something else. So these regions are convex. Why are they convex? Because you can do time sharing. If you can achieve this pair, and if you can achieve this pair, clearly you can achieve this pair by just using this for alpha fraction of time and this for 1 minus alpha fraction of time. Yeah, this is some rate R1, R2 region. So this is a set of all achievable rate R1, R2. So even operationally, the region is convex. So you can characterize the region by supporting hyperplanes, intersection supporting hyperplanes. So I'm just going to look at so now then you have a number for every lambda, and for symmetry I just need to consider lambda bigger than 1. I want to compute what is the maximum over R1, R2, lambda R1 plus R2. So I get the following expression. If the maximum are all input independent distributions of the following form. So this is again the picture that you can do. You do supporting hyperplanes and you're computing the region using supporting hyperplanes. As before, you can see that this region is optimal if and only if the weighted sum rate for the W tensor W is just twice S lambda of W. Yes. For every lambda, for every slope, if it doubles, if and only if characterization. So now you have a number, and it says if and only if it's optimal if and only if it's true. For same argument as before. And why is this true? Again, there's a subadditivity built in. So it's true because this inequality holds. And why does it hold? It's exactly the same proof as before. There's no magic involved here. It's just yes. Yes. No, R of W was, Shannon said that you can, from large deviation, something he said that you can achieve IXY. Typically. Yes. Yeah. Oh, the Q is exactly doing this. Q is kind of a convexification random variable. So if you want to characterize regions, you may need to convexify between points. But if you take hyperplanes, you will not need the Q. So the Q vanishes here. That's important. So see, I don't have a Q here. The Q vanishes because I'm just looking at like an exposed point or extreme point. So I don't need a Q. I don't need to convexify. So it's enough to characterize the extreme point. So no, R1, R2. So how do I get this? So let's go slowly here. So I have this region, right? I want to compute lambda minus 1 R1 plus R2. Say lambda is bigger than 1. I mean, I want to compute lambda R1 plus R2. Lambda is bigger than 1. So I'm going to write this as lambda minus 1 R1 plus R1 plus R2. Okay. This region, if I draw it, will always look like a pentagon for any P of x1, x2. Okay. Which means that to get the maximum for this region, it's enough to look at the first and third inequalities. So that would be the tight constraints. Okay. So which means I want to look at maximization. So I put R1 will become Ix1 y given x2 q, and R1 plus R2 will be Ix1 x2 y given q. And now I just write its maximization over PQ, P of x1 given q, P of x2 given q, of lambda minus 1 times Ix1 y given x2 q plus Ix1 x2 y given q. Now clearly the maximum is bigger than the average, so I can remove the q, and so it just becomes independent x1 x2 of this expression, which is exactly what I have in the next maximum. Clear? So that's how I get. So I start from this expression and get this. Okay. So somebody else gives me a different expression. I start from that expression and compute the hyperplane given by that expression. And I want to show that that particular rate region is tight if and only if this. If and only if this additivity happens, and to show the additivity is enough that the subadditivity happens. Yes. Is that the optimal capacity? Exactly. Yes. That's a litmus test. And in this litmus test is where problems come. Optimization problems come. Yes. No, I just, so you have a convex region, right? And this convex region is always the intersection of supporting hyperplanes, correct? So you can draw, it's the intersection of these supporting hyperplanes. And so each supporting hyperplane is given by some AR1 plus R2, AR1 plus BR2, I mean, let's normalize R2, A bigger or less than 1. Now the symmetry with respect to lambda bigger than 1 and lambda less than 1. So I can just assume lambda bigger than 1. If I use lambda less than 1, then I would take the first, second and third inequalities. So that's, I mean, there's a symmetry in the receiver, so I don't need to worry about it. Okay? Yes. 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 Exactly. Is this the right region or not? It's a decision, yes or no? Yes. Yes, should, I mean, so that the computation question I've not looked at yet, but that's where optimization comes in, right? And I have looked at it in some sense, but I'll tell you in what sense I have, but not in the sense of polynomial. I look in terms of dimensional reduction. Can I do it in a much smaller dimension or not? So, and one can establish in the same way. And another thing you'll observe is that this function is actually also concave in P1 of x1 and P2 of x2. So this is kind of relatively easy because this is concave in the pair of distributions. So if you give me a pair of distributions, I can compute this function from just taking the product distribution and computing the value. So that's also easy. Okay. Now let's look at the broadcast, the dual setting. So here you have a single sender who wants to communicate to two receivers. So there's some message M0 that he wants to communicate to the to both the people. There's a message M1 that he wants to communicate to one of them. M2 he wants to communicate to the other person. So in this sense, maybe a cell phone tower wants to communicate some timing information to both the people and their own messages to each of the receivers. And since there's no feedback, I mean, his decoding decision just depends on the marginal channel Y1 given X, and his decoding decision depends only on Y2 given X. So this is really the broadcast channel. And you can ask, what is the capacity region? So Cathy Martin, she showed that you can achieve a rate triple R0, R1, R2 as long as they satisfy these four constraints. Okay. So this is a very clever use of random hashing to get kind of this constraint. So it's not really, there's some ideas, there are some more ideas than you want to do. So she said that you can achieve this rate, the rate R0, R1, R2, so that if it satisfies these four constraints for any joint distribution. And you can call this region R of WAW. The question is this the capacity region? Again, you can ask the same question, and this has been open. So one of the questions that along there was questions, can I compute this region easily? And so for long times, even when after Cathy wrote the region down, we did not have bounds on the size of U and V. So even if you take binary channels, you do not know, because in this setting there's no U, V, and W, U, V, and Q. So U and V could be potentially infinite. Yeah, you can take a limit of countably infinite, but that's okay. I mean, you can take a limit of countably infinite things, but you still don't know whether, I mean, you can put a finite bound on it. Okay. Oh, so how do you compute the region, you mean? Okay, so the region is very easy. So okay, let's put just R1, R2, okay? So you have, so this goes back to the old say. So let's say you want to compute some R1 less than or equal to something and R2 less than or equal to something, okay? You take your favorite, say P, U, V, Q, X. Okay, you take, and this gives me R1 less than something, R2 less than something, and R1 plus R2 less than something. Okay? Now you take a different P prime U, V, Q, X. You'll give me another region. Right? Because the values may be different, because this depends on the P you choose. Each of these depends on the P you choose. So you have P, so you take any distribution Q, U, V, X. There's a distribution on Q, U, V, X. Okay? You take any distribution on Q, U, V, X. So Q, U, and V are just auxiliary variables. You can just put, okay? So you take a joint distribution. This induces a joint distribution on the entire Q, U, V, X, the outputs which are Y and Z, I think, or Y1, Y2, in the following way. So this is equal to P, U, PQ, U, V, X times WA or channel, W of Y1 given XA and WB of Y2 given. So given X, these are the Markov chain. So this gives